In this video, we are going to discuss the next theory related to coordination compounds, that is called crystal field theory. Crystal field theory. Let's see what are the important postulates of crystal field theory. The first postulate is that the crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic, arising purely from electrostatic interaction between the metal ion and the ligand. So that is the first postulate, that is the CFT, crystal field theory. They consider the bond between metal and ligand to be ionic bond, and it arises from the electrostatic interaction between the metal ion and the ligand. So that is the first postulate of CFT. Now the second postulate is ligands are treated as point charges in case of anions or dipoles in case of neutral molecules. So that is the second postulate, that is it is for ligands. Ligands, they are considered as point charges in case of anions, means if the ligand acts as anion, then the metal will be the cation and the force of attraction will be between the opposite charges. That is the meaning of the word point charge. So the ligands are treated as point charges in case of anion, or they are treated as dipoles. The ligands are treated as dipole in case of neutral molecule. Means if the ligands are neutral molecule, then neutral molecule means NH3, water, etc. Then in that case, the negative end of dipole, if it is NH3, it is the nitrogen atom that is negatively charged. If it is H2O, it is oxygen atom that is negatively charged. So if the ligand is a neutral molecule, then the negative end of the dipole is attracted to the central metal atom. So that is the second postulate, that is regarding ligands. Ligands are considered as point charges in case of anion or as dipoles in case of neutral molecule. Now the third postulate is a very important postulate based on which the CFT is studied. The 5 D orbitals in an isolated gaseous metal atom or ion have same energy, that is, they are degenerate. This degeneracy is maintained if a spherically symmetrical field of negative charge surrounds the metal atom or ion. When this negative charge is due to ligands in a complex, then it becomes asymmetrical and the degeneracy of the d orbital is lifted, and it results in splitting of D orbital. That is the third postulate. That is, we know that there are 5 D orbitals. What are the 5 D orbitals? The D orbitals are named as dxy, dxz, dyz, dx square minus y square and dz square. These are the 5 D orbitals, and you know these 5 D orbitals are degenerate. What's the meaning of degenerate? Degenerate means same energy. So if the orbitals have same energy, we can use the word degenerate. So the 5 D orbitals are degenerate. Now when do these 5 D orbitals are degenerate, or when do they have the same energy? In free metal atom, means the metal atom is free. It has not formed a bond with the ligand. Okay, so in the case of free metal atom, the 5 D orbitals are degenerate. But when the ligand comes, or in the presence of ligand, what happens to the degeneracy of the 5 D orbital? The degeneracy of the 5 D orbital is lifted, which means the energy of the 5 D orbitals will be lifted. It will be raised a little. And when the 5 D orbitals are raised in energy, it results in the splitting of D orbitals. Okay, so in the presence of ligand, the degeneracy of the 5 d orbitals is removed and the d orbitals get lifted in energy. As a result, what happens? The d orbitals will split. The 5 d orbitals, now they don't have the same energy. Now you cannot call them a degenerate orbital. They don't have same energy in the presence of ligand. So next we are going to see the crystal field splitting in octahedral coordination entity. Means why this d orbital gets splitted in the presence of ligand, or why or how the degeneracy of the d orbital is lost in the presence of ligand. So these are the 3 postulates of crystal field theory. So next we are going to see the crystal field splitting. Crystal field splitting in octahedral coordination entities. Now, before we discuss the crystal field splitting, we have learned the shapes of 5 d orbitals in class 11. We know that the shape of, we have the shape like we have lobes, and in the case of dxy, dyz and dxz, now we have in these 3 d orbitals the lobes lying between the axes. For example, if you are drawing dxy orbital, this is x-axis and this is y-axis, then this dxy is shown like this. The lobes are lying between the axes. Now, in the case of dx square minus y square and dz square orbitals, their lobes are lying. Lobes are lying along the axis. Okay, so dx square minus y square, if you are asked to draw, where are the lobes lying? X-axis, y-axis. The lobes are lying along the axis. So this you have to keep in mind. Okay, so the 5 d orbitals, 3 d orbitals, that is dxy, dxz and dyz, they have their lobes lying in between the axis, and dx square minus y square and dz square have their lobes lying along the axis. Now, what will happen? We are studying about the d orbital splitting in octahedral coordination entity, which means we have the coordination number 6 and the shape is octahedral. Now, in the presence of ligand, now in the beginning the central metal atom has only d orbitals and the 5 d orbitals have same energy, or they are degenerate. But what happens when the ligand comes to the metal atom? There will be repulsion of electrons. Between whom? There will be repulsion of electrons present in d orbital of the metal atom with the electrons of the ligand. Okay, so what will happen as a result of this repulsion? Now, this repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. So, the dx square minus y square and dz square orbital who has their lobes lying along the axis, they point towards the axis along the direction of ligand. Their orbitals will point along the axis, towards the axis along the direction of ligand. They experience more repulsion. That means the electrons present in dx square minus y square and dz square orbitals will experience more repulsion from the electrons of the ligand, and they will be raised in energy. Okay, so dx square minus y square and dz square orbital in the presence of ligand will be raised in energy. And what happened to the other 3 ligands? The other 3 metal orbitals, D orbitals, dxy, dyz and dxz orbitals which are directed between the axes will be lowered in energy, and we can say that the degeneracy of the d orbital is removed. Why? How is the degeneracy of the d orbital removed? Due to metal electron and ligand electron repulsion in the octahedral complex, and it results in the splitting of d orbitals into 2 sets. So, in the presence of ligand, the degeneracy of the d orbital is lost. And what is the reason for that removal of degeneracy? Due to metal electron and ligand electron repulsion. And what happens when the degeneracy is lost? The metal d orbital will split into 2 sets. One set will be of higher energy and the other d orbital will be of lower energy. So, it results in the splitting of d orbitals into 2 sets. Now, we have 2 sets of d orbitals. Which are the 2 sets of d orbitals? One set is dx square minus y square and dz square, and the other set is dxy, dyz and dxz. Now, this set is of high energy, and you can call this set as, this set is called Eg set, Eg. And this set is of low energy, and this is called T2G set. Okay, so this is the splitting of d orbital in octahedral coordination entity. So, I will explain it again. In the presence of ligand, what will happen? There will be metal electron, ligand electron repulsion. As a result, the degeneracy of the d orbital is removed, which results in the splitting of d orbitals into 2 sets. One set, there is dx square minus y square and dz square, which has higher energy, is called Eg set, and the other set dxy, dyz and dxz with lower energy is called T2G set. And we call the splitting of degenerate orbitals, d orbitals, in the presence of a ligand as crystal field splitting. Crystal field splitting. So, what do you mean by crystal field splitting? Crystal field splitting is the splitting of degenerate d orbitals in the presence of ligand in a complex is called crystal field splitting. And when they split, there will be energy separation between these 2 sets, that is between T2G and Eg. That energy difference is called crystal field splitting energy. So, the next term is crystal field splitting energy, or this can also be called crystal field stabilization energy, or the short form is CFSC. So, what do you mean by crystal field splitting energy? The difference in energy between 2 sets of d orbitals, or the difference in energy between Eg and T2G is called crystal field splitting energy, and this is denoted by delta O. Now, here this O, it is not 0, it is O. O stands for octahedral. We are studying the crystal field splitting in octahedral coordination entity. Okay. Now, here I have drawn the orbital, d orbital splitting in octahedral crystal field. You can see the d orbital splitting, and here you can see energy. The energy is increasing in this order. Now, here the d orbitals are indicated by lines instead of the orbital diagram, square boxes. I have marked here with lines. These are the 5 d orbitals of free metal ion. Now, what happens in the presence of ligand? The energy is lifted. So this is the average energy of d orbitals in the crystal field, and it results in splitting of d orbitals into two sets. One low energy T2G. This is our T2G. And which are the T2G? Set dxy, dxz and dyz. And high energy EG. This is our EG set, and we have dx square minus y square and dz square orbitals in EG set. Now here the center is the average energy level, and it is also called barycenter. Barycenter means the average energy level. Also you can see the energy of EG set is raised by 3 by 5 delta O above the average energy level, and the energy of T2G set is reduced or lowered by 2 by 5 delta O below the average energy level. Okay, and this difference, you can see this difference, there is difference in energy between T2G and EG, is called our delta O, that is crystal field splitting energy or crystal field stabilization energy. Okay, now this 3 by 5 delta O means it is equal to 0.6 delta O, and 2 by 5 is 0.4 delta O. No need to write 0.6 and 0.4, you can write it as 2 by 5 delta O and 3 by 5 delta O. So this is a very important diagram, usually asked for board exam. Draw the d orbital splitting in octahedral crystal field. Everything should be marked, okay, properly. Now again, the magnitude of crystal field splitting or crystal field splitting depends upon the ligand strength. Here comes our strong and weak ligand. Okay, so how far the splitting or that crystal field splitting energy, what is the value, all these depends upon the strength of the ligand. If it is a strong ligand, if the ligand is a strong ligand, then the d orbital splitting will be very large, and if the ligand is a weak ligand, then the d orbital splitting will be very small. So strong ligand means or strong field if they produce means it's a strong ligand in which the d orbital splitting is large, and weak ligand means the d orbital splitting will be small. Okay, now ligands, based on their splitting, whether they produce a strong splitting or a weak splitting, the ligands are classified or they can be arranged in a series in the order of their increasing field strength. So the ligands are arranged in increasing order of their field strength, and we call that series as spectrochemical series. And you can see I have written the spectrochemical series on the board. Now in the series we have I minus less than Br minus less than Scn minus less than, halide ions are here, then OH minus, oxalate ion. After oxalate ion we have H2O less than EDTA4 minus, ammonia, ethane 1,2-diamine, cyanide ion, and finally last we have CO. Okay, so this is our spectrochemical series. Now when you look at this, this is arranged in increasing order. So which is the strongest ligand in this? The strongest ligand here is our CO. This is the strongest ligand. Or this is the strong ligand. And the weakest ligand in the series is I minus. I minus. This is the weakest ligand. Or generally it is said that the ligands coming before water, that is the halide ions, then you can see OH minus, oxalate ions, they are all weak ligands. So ligands coming before water in the spectrochemical series are all weak ligands, and ligands coming after water, they are all strong ligands. Ammonia, we already discussed under valence bond theory. Ammonia is a strong ligand. Ethane 1,2-diamine is a strong ligand. Cn minus, CO, all these are strong ligands. Now here you have to check out for this oxalate ion. When we discussed in valence bond theory, the questions, oxalate ion is considered as a strong ligand. But actually it's a weak ligand because it's coming before water. But in your 12th standard, we are considering that oxalate ion as a strong ligand. Also, water is a weak ligand. Okay, so this is spectrochemical series. So what do you mean by spectrochemical series? The arrangement of ligands in increasing order of their field strength is called spectrochemical series. And strong ligands will produce large splitting and weak ligands will produce small splitting of d orbitals. Okay, now next I have drawn the d orbital splitting in tetrahedral crystal field. Now in tetrahedral crystal field means we have the coordination number is equal to 4, but we don't have much to study under tetrahedral crystal field, just the d orbital splitting diagram is needed. Now if you look at this diagram, you can see that the d orbital in free ion, this is the d orbital, and in the presence of ligand it's raised in energy. So this is the average energy of d orbital. It's split into two sets. Now we can see that the set here is E and T2. Now here E is of lower energy and T2 is of higher energy. Now we don't use the word G. In octahedral we had EG and T2G. Here we don't use G, and here the low energy set is E and high energy set is T2. Now also you can see the difference in energy between E and T2 is delta T, and here T stands for tetrahedral. Now the energy of E is reduced by 3/5 delta T and energy of T2 is increased by 2/5 delta T. And the sets d orbital with E is dx square minus y square and dz square, and T2 is dxy dyz dxz. So everything is same except that the d orbital splitting is inverted. E will come down and T2 with higher energy. Okay, so this is the d orbital splitting in tetrahedral crystal field. So with this we complete the splitting diagram, d orbital splitting diagram in octahedral and tetrahedral crystal field, and also we saw that there are strong and weak ligands which are arranged in increasing order of their field strength, and the strong ligands will give large splitting of d orbital and weak ligands will give small splitting of d orbitals. Now we are going to study in detail about the strong and weak ligands, or how they influence the splitting of d orbitals in octahedral complexes. We will see in the next video. Thank you.